Dear friends of thermodynamics, I am Markus Lohmeier from FAU and I'm speaking about exergetic Port-Hamiltonian systems and in particular about the prototypical model in non-equilibrium thermodynamics, the Navier-Stokes-Fourier fluid. I got interested in thermodynamics when reading about thermoacoustic cooling systems, which can be powered by solar thermal energy or waste heat. Such cooling systems comprise a resonator, a number of thermoacoustic prime movers which amplify an acoustic wave that in turn powers a number of thermoacoustic refrigerators. Such thermoacoustic devices and other technologies for low temperature energy conversion are typically based on the Stirling cycle. While studying the literature on Stirling cycle devices, I observed that a framework for optimization and control-oriented modeling was missing. Mathematical models employed by researchers in the field typically merely predict steady states of a linear dynamical system. Moreover, the thermodynamic consistency or meaning of such models is not obvious. My research interest then shifted towards the development of an appropriate modeling framework, which got me interested in geometric mechanics, non-equilibrium thermodynamics, and applied category theory. On the right, you can see a representation of the compositional structure of a model of a classical Stirling engine. An appropriate framework would help to tame the complexity of realistic models with a modular and hierarchical approach. Imagine that the 9 subsystems are themselves defined in terms of subsystems. The thermodynamic consistency of all subsystems would imply the consistency of the resulting composite system. Diagrams similar to those on the right would be expressions in the syntax of a formal modeling language, which enables effective communication between scientists, engineers, and their software tools. Finally, to assess performance and efficiency, engineers usually prefer exergeometrics, which can be intuitively defined and understood based on such diagrams. Given that the interaction between two connected systems is associated with an exchange of exergetic power, it seemed that such a framework could have a considerable value even outside the field of sustainable energy systems. The equivalence between interaction of systems and exchange of power led me to Port-Hamiltonian systems, which can be intuitively visualized as bond graphs. A Port-Hamiltonian system in general comprises 3 kinds of structures, representing energy storage, energy routing, and dissipation. The structure is preserved by power-preserving interconnection. Further, there is a growing body of literature on structure-preserving model transformations such as discretization methods. I was quickly convinced that Port-Hamiltonian systems theory is an adequate basis for the modeling framework that I desired. But as an unhoped-for surprise, the literature on Port-Hamiltonian systems seemed rife with confusion about modeling thermodynamic systems. Moreover, some researchers from the Port-Hamiltonian community developed 3 quite distinct frameworks for modeling thermodynamic systems. These are, however, rarely understood by researchers in the Port-Hamiltonian community, and consequently it is widely believed that the Port-Hamiltonian framework is not sufficiently general for modeling thermodynamic systems. Fortunately, though, this is not the case. There is a non-trivial intersection between Port-Hamiltonian systems theory and the generic framework of non-equilibrium thermodynamics. When I turned my attention to this intersection, the desired modeling framework started to reveal itself more clearly, and I chose the name Exergetic Port-Hamiltonian Systems, or EPHS for short, to refer to it. An isolated EPHS can be boiled down to a generic model with local thermodynamic equilibrium. Before I speak about the fluid model, I want to devote some time to basic ideas behind the EPHS framework. After presenting the fluid model, I will briefly comment on future work. The general equation for non-equilibrium reversible-irreversible coupling, for short the generic, is defined by 5 building blocks: a state space X, an energy function E, an entropy function S, a skew-symmetric tensor L, and a symmetric positive semi-definite tensor M. The first term in the generic defines a Hamiltonian dynamics, and the second term defines a gradient dynamics. For every x in the state space, L and M seen as linear operators from the cotangent space at x to the tangent space at x have a kernel such that the first and second law of thermodynamics are structural properties of the generic. The generic can be interpreted as a dynamic statement of the maximum entropy principle. Making use of the null spaces of L and M, the generic can be written in terms of a single function phi, which is a Lyapunov function for the stability of the thermodynamic equilibrium state x0. Phi can also be seen as the Lagrangian for entropy maximization, under the constraints of constant total energy, volume, and mass. Another interpretation of the generic has received little attention so far. If we consider our system of interest together with an environment of constant temperature, pressure, chemical potential, etc., we can interpret the single generating function A as the total exergy of the system with respect to the chosen environment. Since the system of interest and the environment need not interact, augmenting an environment to the system ensures no loss of generality. The exergy metric quantifies the amount of work that the system can do at a macroscopic level. If we interpret A as a Lagrangian, we see that exergy is the maximum amount of energy E at the state x minus E at the equilibrium state, which can be reversibly extracted from the otherwise isolated system. Simply adding ports leads us to the primordial exergetic Port-Hamiltonian system. Thus, we have a clear structure and thermodynamic interpretation for models of open multiphysical systems. However, to become an appropriate basis for software tools used by scientists and engineers, the EPHS framework needs a rigorous way to communicate the compositional structure of complex models. This is achieved by a formal syntax defined as an operad. The image on this slide represents a typical expression in the EPHS syntax. It states the composition pattern of a model of a non-isothermal damped oscillator. The outer box of an expression represents the boundary of the respective composite system, while the inner boxes represent its subsystems. As common in thermodynamics, the syntax follows the sign convention that power going into a system is counted positive. The junctions represent physical domains. For instance, the box dm represents a reversible coupling between the potential energy domain on its left and the kinetic energy domain on its right. Hence, the net exergetic power at the box dm is 0. In contrast, the box labeled damping represents an irreversible coupling between the kinetic energy domain above and the thermal energy domain below. The net exergetic power at the box is an exergy destruction rate, and hence it is non-negative. At every junction, the flow variables of all adjacent ports sum to 0, while the effort variables are equal. I will briefly discuss three subsystems of the model. If we have a function u for the internal energy of the thermal capacity, we know its exergetic Hamiltonian. The flow variable is a rate of entropy change, and the effort variable is the temperature relative to the environment. Locally, the change of entropy is the inverse temperature multiplied by the change of energy. It follows that the pairing of the effort and flow variables equals the Carnot efficiency times the rate of change for energy in the thermal capacity. This confirms that exergy is the amount of energy that can be extracted by an ideal conversion device interacting with the system and the chosen environment. The damping model is a resistive structure if we view the matrix appearing in its definition as a tensor on the state space of the entire system as in the generic. The definition of the damping subsystem would be entangled with the definition of the thermal capacity, which makes little sense from a compositional perspective. We instead view the damping model as a nonlinear map, taking effort variables to flow variables. The effort variables give rise to thermodynamic forces, while the flow variables result from thermodynamic fluxes. The nonlinear map can nevertheless be written in the form of a matrix vector product, which allows us to easily assert its structural properties. First, the symmetry of the matrix is the Onsager symmetry. Second, if we replace the shifts by the environment temperature θ0 written in blue with 0, the flow variables evaluate to 0 too, which is a simple way of asserting that a resistive structure conserves energy. Finally, the positive semi-definiteness of the matrix asserts that the entropy production or exergy destruction rate is non-negative. The same holds, of course, for the heat transfer model. If we factorize its matrix in this way, we obtain a completely straightforward correspondence between our lumped parameter heat transfer model and a distributed parameter EPHS model of thermal conduction, stated in the exterior calculus formalism. This also shows that the exterior calculus formalism helps us to reason about how to mimic smooth geometric structures in a discrete setting. Before talking about the Navier-Stokes-Fourier model, I want to speak about the work that has led up to it. In 2001, Van der Schaft and Maschke wrote the Euler equations for an ideal fluid in Port-Hamiltonian form. In 2018, Badley and Maschke, Beatty and Meermann rewrote the generic model of a Navier-Stokes-Fourier fluid in a monolithic Port-Hamiltonian form. In fact, their work should be seen as the first step towards the EPHS framework. In 2021, Rashad, Califano, Schuller and Stramiccioli discussed a principled derivation of the ideal fluid model of Van der Schaft and Maschke via Lie-Poisson reduction. In the same year, they extended the model with a resistive relation modeling fluid viscosity. However, by assuming a barotropic fluid, their decomposed model completely ignores the thermal domain. The presented compositional thermodynamic model provides a synthesis of these works. The model can be split into 5 subsystems. The 2 subsystems on the left are related to storage and exchange of kinetic energy and internal energy respectively. Their interconnection yields the ideal fluid model. The 3 subsystems on the right are of dissipative nature and can be added to the ideal fluid model independently of each other. They model thermal conduction, bulk viscosity, and shear viscosity. The box HK represents storage of kinetic energy, and DK represents the Stokes-Dirac structure, which is derived from the Lie-Poisson structure of the original Hamiltonian model of an ideal fluid. The external port P is related to momentum exchange inside the domain. The flow variable is the force acting on the fluid, while the corresponding effort variable is the fluid velocity. The external port BK is related to kinetic energy exchange across the domain boundary. Its flow variable is the mass flow rate, and its effort variable is the specific kinetic energy. Since time is short, and since some of you might not be familiar with the exterior calculus formalism, I choose to skip the defining equations. The box HI represents storage of internal energy, and DI represents the reversible coupling between the fluid motion and the advected quantities entropy and mass. The external port S is related to entropy exchange inside the domain, and it is required to connect the dissipative subsystems. Its flow variable is the rate of entropy change, and its effort variable is the temperature relative to the environment. The port P has the same meaning as discussed for the previous subsystem. Ports BS and BM are related to the advection of thermal and chemical energy across the domain boundary respectively. The flow variables are the entropy and mass flow rate, while the effort variables are the relative temperature and relative chemical potential. The box RT represents the thermal conduction process. The external port S has the same meaning as discussed for the previous subsystem. The port BT is related to thermal conduction across the domain boundary. Its flow variable is the entropy flux, and its effort variable is the relative temperature. The box R1 represents the relaxation process called bulk viscosity. Ports P and S have the same meaning as discussed for previous subsystems. The port B1 is related to the exchange of kinetic energy through bulk viscous forces acting across the domain boundary. Similarly, the box R2 represents the relaxation process called shear viscosity. However, since shear stress cannot be described by ordinary differential forms, another duality pairing is necessary, and the box D2 is essentially an adapter between the different pairings. Before I end with an outlook on future work, I want to assure you that the compositional model boils down to the following equations which hold inside the domain, together with the boundary conditions defined by the boundary ports BK, BM, BS, BT, B1 and B2. The compositional structure is stated in the EPHS syntax, while the equations defining primitive subsystems belong to an EPHS semantics. The map from syntax to semantics is a functor. The functoriality here means that it makes no difference whether we first compose the syntactic expressions and then assign semantics, or if we first assign semantics to individual subsystems and then compose the obtained results. Future work should clarify how to define mimetic spatial discretization as a natural transformation between distributed parameter EPHS semantics and lump parameter EPHS semantics. Naturality here means that it makes no difference whether we first compose the subsystems and then discretize the composite system, or if we discretize the subsystems individually and then compose them as lump parameter systems. With that, I want to thank you for your attention.